All right, good afternoon, everyone. Welcome back. We've got a great afternoon for you, and the next speaker is actually a real treat. I have seen him talk at other events, and it's definitely impressive. You know, when you think of Netflix, it's not the first company that comes to mind when you think of open source software. But if you think about it, Netflix business is really, you know, content. There are the movies, the data that they have about their users' viewing habits and the users themselves. And after that, I think they pretty much open source everything else. No kidding. And so we have Adrian Cockcroft from Netflix here who's going to explain just how much of a power user Netflix is when it comes to open source. So welcome, Adrian.
Where's the clicker?
Don't forget the clicker.
I need the clicker, right. Need somewhere to put this that doesn't fall over as well. All right. Okay. Thanks for having me here. And I'm going to talk a bit about what I call dystopia as a service. So I'm going to start off talking about what do I mean by dystopia in the first place. And then cloud native as an architecture that Netflix is currently using, and Netflix OSS, which is our open source platform, which basically helps people build cloud-native architectures. And at the end, I've got some opportunities and things that I think are particularly relevant to the Linux Foundation, the kind of things that I'd like you guys to be thinking about as how the open source projects you build interact with the things that we're trying to do. So to start off with, you know, we're all engineers, right? And what engineers do is they solve hard problems. We build amazing and complex things, and we fix things when they break. I mean, that's sort of guts of what engineering's about. And to do that, we're always striving for perfection. We want to have perfect code running on perfect hardware and operated in perfectly and nothing ever goes wrong. And that's kind of the engineering nirvana, the engineering utopia. The trouble is that that takes too long. So we end up compromising. There's always time to market. I'm sorry, yeah, you've got the bug rate down to a low enough level. We'll ship it now. And it's time to market versus quality is a trade-off that we're always making. And this utopia is always slightly out of reach. And if you always try to get to the utopia, then you end up compromising by taking an extra month or two, you know, to make the code a bit better. And then eventually you get your product out to market, and it's still got a few bugs in it, but you're trying to get to that endpoint. There's another way of going, which is to basically say that if we take, instead of trying to build perfect software, we try and build as fast as possible. And this is where time to market matters. And there are a number of marketplaces or environments where it matters a lot how fast you can go. And as we've migrated from the world of packaged software, where you ship somebody a CD or a tape or something, to web services where you're using a service it can update all the time, we're basically building those out of agile infrastructure. This is basically what cloud is. And we're doing continuous deployment to those. So we're continuously updating our systems. We're continuously redeploying the hardware it's running on. And we're building things that our customers use directly as web services. So in this environment, it's all about time to market. And what I really mean here is moving that from, you know, instead of trying to build utopia, it's like, well, how fast, how soon can you build something? And what we want to do is have code features from having an idea to shipping that idea to customers in days rather than months. We want to deploy new hardware in minutes rather than taking weeks. And we want to have an incident response that tells that something's broken and automatically fixes it, or tells us in seconds rather than taking hours to fix everything. So that's kind of where we'd like to be. And unfortunately, that means we don't have time to go through all of the trying to make everything perfect. So we end up with something that looks a bit like this. We don't have time to make it cheaper, so we run inefficiently. We don't have time to make it better, so we run with things that are a bit broken. We don't have time to lock everything down and get it perfect, so it can be static and stay the same for a long time. So we make it dynamic. We continuously change everything. But that means we get everything a lot sooner. And that's the dystopia that we basically end up living in. And instead of that nice, perfect Linux running on a nice, perfect machine, running in your nice, perfect application, we're running a continuously changing, confusing, chaotic mix of things which somehow manages to work. So I'm going to talk a bit about how we get that to work. So this is really a new engineering challenge, if you like. We're trying to construct a highly agile and highly available service from ephemeral pieces and often broken components. So at any point of time, there is a lot of brokenness in our systems, and the service we're working on is working anyway. So we call that cloud native. And as an example, I'm going to explain how Netflix works as a cloud native application. So this is the home page. If you use Netflix, you see something that looks like this. There's a few rows of movies. There's what I was watching recently, some other stuff that the Netflix thinks I might like, and some things my friends have been watching recently. So that's a normal experience. So the question is, how does that actually work behind the scenes? What we have is a series of services. The blue box on here is your consumer device, your browser, your TV set, whatever it happens to be. Lots of Samsung TV sets, for example, going from this morning. Behind that, all of those orange boxes are running as cloud-based services. These are running on AWS. And the red box there is our OpenConnect CDN service. And those are distributed differently. They don't run within the Amazon service. So what we have is a set of web services that tell us about our customers. And that's how the personalization system works. When you hit play, once you've figured out which box shot you want to push the play button on, you're then talking to the streaming service, which does DRM and logging and quality of service management, and figures out where the files that are needed to stream that movie live. And then they point the browser or the replay device at our CDN. And that CDN is being fed in the back end by a whole lot of control software that manages what's on it and makes sure everything's working right. And also, it takes a feed of new movies that as we license them from studios and whatever, those come in, they're encoded. So the back end for all of this is running on the cloud. And there is no data center in the back of this. This whole system is completely ephemeral. It's completely deployed as a cloud-based service. That content delivery service looks like this. This is one of our open source projects. It's an open source hardware design, and then it runs, basically it's just a big static content web server. We have a large number of these deployed, and we open source the whole thing around it. One question I have for the Linux Foundation is, so why did we do this with FreeBSD? Right. And it's a question for you guys. Why is it that most of the large-scale networking things out there are still being built with BSD rather than Linux? I think there's probably some work to be done in the area of network compliance or network performance or something like that. So I'd see that as a weakness for you guys to go figure out how to improve somewhere. Because this is kind of the state of the art. You find most of the large-scale networking systems are still running on BSD rather than a Linux platform. Anyway, so we have enough of these things out there, plus the commercial CDN providers, that this is what our traffic looks like. This is from November last year. We're about a third of the downstream traffic that's going to US fixed traffic. So this is to houses, and that's, thanks for building the internet so we could fill it with movies, is basically the summary there. And most of our competitors are a long way down the list, so that makes us happy. The upstream bandwidth is us doing quality of service logging and a lot of other stuff, to keep track of everything. And I'll come back to this because we really are doing a large amount of instrumentation of our systems to figure out what's going on. Okay. So I showed you the big block diagram version of what's going on. This is an actual view of the Netflix homepage. So that page I showed you that had with the movie shots on it, this is the internal architecture of Netflix for the services that are involved in generating that page. So where it says start here, that's actually something like 500 to 1,000 web server machines. They're all, I think, currently sort of 32 gigabyte Tomcat servers, something like that. They talk to many services behind them, tens of services behind them, which talk to more services, which talk to more services. So in the second or so that it takes us to generate everything that's on that home page, this is what the fan out looks like internally. This is the set of services that get called. Some of them are Cassandra services that provide data. So a lot of the ones that are gray on here are memcached. The green ones are Java code. The gray ones are running something else. And then we have web services, S3 buckets, all kinds of different endpoints. The big concentrated one at the bottom right is something that generates which lists of movies are relevant for this customer. And there are multiple versions of that. Now, each of the icons on here isn't a single machine. It's a single service type. And that service type is distributed across 3 data centers, 3 Amazon availability zones. And there are at least 3 of anything that's on this diagram, but typically there are hundreds of them. So what you're looking at here is several thousand machines are involved in managing just responding to the home page. And this is for a single request. This is just hit the home page. This is what it takes. Right? So to deploy that, if anything goes wrong, we just, let's say that service dies for some reason or somebody pushes bad code to it. One of the rows on the home page doesn't appear or some piece of data is not quite as good. So it gradually degrades. You don't suddenly have no home page to talk to. It sort of becomes imperceptibly worse than it would have been if that service was working. So this is kind of another way of looking at that architecture. We have 3 columns of systems here running in Zone A, Zone B, and Zone C. The traffic comes in from the top, from the things, whatever the end customer devices are, and that's spread across many layers of services, mostly JVMs, but a few memcaches and things like that. And those are all stateless services. Memcache is in memory, but it's, so if you kill one, you just start again, start refilling it. And then behind that, we have Cassandra giving us a quorum-based NoSQL data store. So that's our persistence tier. And if anything goes wrong with any one service, obviously, we can keep going. But we can actually take the loss of an entire building. So many classes of failures, we basically aggregate up and say, OK, this whole zone's gone, the network's gone, the power's gone, something's wrong with every machine in this building. We can continue to run the entire service on 2 out of 3 buildings, 2 out of 3 zones. Now, we actually test this, and a few weeks ago, we ran what we call our Chaos Gorilla. We have a Chaos Monkey that kills individual services. We have a Chaos Gorilla that takes out an entire zone, and we ran that on production a few weeks ago and deliberately killed 1/3 of our infrastructure. At the time, that morning, it was several thousand machines were shut down, and everything kept going. There were a few errors here and there. We found a few things that weren't exactly right in the system, but then we put them all back and kept going. But it wasn't a major outage for Netflix customers. So the only way you can do this is to prove that this works is by actually doing it in production. So these are the new anti-fragile patterns. You start off with microservices, single-function services that have a REST interface that do one thing and call other services. You run chaos engines like the Chaos Gorilla, the Chaos Monkey that go around trying to break things to prove that everything is resilient to it. And then you end up building these highly available systems out of ephemeral components. So I'm just going to look briefly at what the architecture of these individual components are. The stateless microservice that we have 10,000 of, it's a Linux-based AMI almost entirely. There's a few other bits and pieces in there, but this is the core of the pattern, which is currently an old version of CentOS, like 5.5 or something, running some ancient Linux kernel from 3 or 4 years ago. We're trying to get onto a more recent Ubuntu. And then we have Java, which is mostly JDK 7 at this point, and a few bits of JDK 6 and a bit of OpenJDK, sort of all mixed in there. That runs 1 copy of Tomcat that fills up the entire machine, and that's typically between sort of 5 gigabytes and 30 or 40 gigabytes. We have a few of these systems running on 50, 60 gigabyte footprints. So big, fat Tomcat server that's got lots of Java code, lots of caching, and a lot going on. So you just replicate this 5,000, 10,000 times, and that's basically most of what Netflix is. Now, for the persistence layer, it's a little different. We've still got the base AMI. We still have Java, but we have 2 copies of Java here. One is running our own management service we call Priam, which in Greek mythology, Priam is Cassandra's dad, and sort of controls whether she can go out at night and what she should wear and all that kind of stuff. So basically controls Cassandra, which is the service that's giving us persistence. And the green blob at the bottom, I want to be really clear here, we don't use any attached storage. I'm not using any commercial off-the-shelf or whatever storage services in this. I'm using the internal disks that came with the AWS instance. And we've been moving gradually from using just the spinning Rust. You know, you get 1.6 terabytes on 2 drives. You can just about run on that if you're careful. And what we've been doing in the last year is moving to solid-state disks. So then you get 2 terabytes. You can do a gigabyte a second to that. It works very nicely. So we have hundreds of machines now running solid-state disks in the cloud, and that's the foundation service that Netflix runs on. So this is the basic concept of being cloud native. First of all, the master copies of all our data are cloud resident. This isn't a copy of stuff in our data center. We don't call back to the data center to get our subscriber data. The master copy is in the cloud. We do backups and archives in the cloud, and we can restore everything and scale everything in the cloud. Everything is dynamically provisioned. You just click a button, 10 minutes later, I have a new Cassandra cluster. That's how long it takes. I don't care whether it's 100 nodes and how many tens of terabytes or hundreds of terabytes I need. I can do that in minutes. And all the services are ephemeral. When we killed off a third of our infrastructure in the Chaos Gorilla test, we killed off a third of our Cassandra nodes as well. So we were running just on 2 out of 3 for a while until we put them back. So we'll talk a bit about what that looks like from a scalability and dynamic. You know, this isn't just a fixed architecture where you build it once and walk away. It's dynamic. It keeps changing. This is the tool we built. That's one of our open source projects called Asgard that we use for deploying code. And this is trying to show you what it's like to deploy code. I have a cluster running the old code. I have a cluster running the new code. I push a button to enable it. The traffic switches over, and I'm now running on both. And then I turn off the traffic to the old one, and I leave it there. So I don't deploy code to a machine. I deploy new machines. Right? I deploy a completely new cluster, a completely new autoscale group, and I have what we call an application is actually a sequence of autoscale groups that makes up a big cluster. When I want to deploy code again, I pick a new instance type. It's a baked AMI. I basically say how many of them I want. I fire them up, and once they're nice and warmed up and ready, I switch traffic to them. We typically run overlap for several hours in case we find a problem in the code. And if anything goes wrong at the point where you send traffic to this new system, we have monitoring that responds in seconds. So we can see within just a matter of 2 or 3 seconds that something bad is happening. We can push the button again and switch back again in seconds. So we can do manually tell that something's gone wrong in seconds, and we have automation that will do this for us as well. So this is what it looks like if you're at one of the services. This is just one of those dots on that diagram I showed you, where we have 500 or 600 of these at peak. And starting in the morning, we start adding more. We're auto-scaling up because as they get busier, they automatically add more machines. Once we've got 600 or so machines, we run through peak, and then as it gets to be later at night, people stop watching movies, and we auto-scale back down again to a minimum level. And then over on the right, you see a sudden spike in the morning that roughly doubles the capacity. That's us basically doing a code push. We started the same number of machines again with the new code in it, and we put those both into traffic. So that's the typical day in the life of a set of systems here. And you can see a lot of these instances, half of the machines are only there for a few hours through peak. And across a large collection of our systems, the average lifetime is a day and a half. Within about a week, you're putting new code on it. And if you're auto-scaling, then systems only live for half a day or a few hours on average. So the average across everything is a day and a half. So I really only need my machines to be running for a short period of time. Now, we do have a long tail of systems that run for months, but the bulk of our traffic is on these very short-lived systems. So one of the things that we've been working on this year is dealing with multiple region availability. If anything goes wrong in a zone, we can handle it. But if anything goes wrong in a region, which is for us is 3 zones, then we don't have currently got a way of handling it. And some of the outages that you may have heard about from last year are caused by zone-level outages, which are a mixture of us having problems or AWS having problems or networking having problems. So what we're trying to figure out now is how to run across multiple regions and switch traffic back and forth. So you have a customer, and you have to connect that customer to the traffic. And The typical way you do that is with DNS, and there are all these nice DNS vendors who all have wildly incompatible APIs, somewhat overlapping feature sets, and we basically said we need and they're all designed to be hand-managed one thing at a time by your network engineer who, you write a ticket and he goes there and logs into the console and carefully pokes a button and then, does whatever he does to, praise to somebody that he got it right and pushes the button and hopes he didn't screw up DNS for everything, because you can kill everything very easily. So what we're doing to deal with this is we're building a wrapper around this we call Denominator. This is one of our most recent open source projects. This is one of the ones where we've actually been building it in public. I mean, a lot of the time you build open source, you build code, and then at the end of it, it's running, okay, let's open source that thing. So you sort of tidy it up a bit, put a bow on it, and write a tech blog post and stick it on the site. This was different because we had the idea in public. We had to collaboratively work with the DNS vendors to build this, and we've been writing the code in public. So the first version of this didn't really run at all. And the first code we put out there on GitHub, and we just had 1.0 come out recently, which has some pretty useful support. So if you're messing around with DNS and you want a multi-vendor pluggable DNS API, this is a Java library which abstracts that. It's also a command line wrappable thing, so you can actually use a command line version of this and script it as well. So this is a really hard problem, it turns out, because those APIs are all horribly broken one way or another. The Route 53 API is actually quite nicely structured, but it's just missing most of the features we need to use, and the other two APIs really are quite badly broken. So the lesson I'd put up from this is, if you're developing APIs to things, please build clients for them and find out how hard that is before you just put it up. Don't just stick a web page on it and assume you're done. It's building automation to manage things like SDN and software-defined networking and other constructs. It's really important to get the API right. And there's some good books on how to do good APIs, but there are an awful lot of bad APIs out there. And we're trying to just paper that over with this, and it's turning into a much harder problem than it should have been. So these are all parts of what we call Netflix OSS, which is our open source software platform. We brought this out. We started releasing this last year, one piece at a time, and the pieces didn't really fit together or make sense because they were sort of the foundation bricks. And you're trying to look for a house, and all you see is a pile of bricks and a few foundations. What we've actually been doing more recently is bundling it together a bit more, and we now have most of the parts to make it look like a complete platform. So this is the brand we've put on it, effectively, to make it more platformy. And there's a bunch of inspiration for this. The Release It book by Michael Nygaard is one of them. I mean, hopefully you've seen these. I haven't really have time to go through all this. But Anti-Fragile is another one. Thinking in Systems, a lot of complexity theory and feedback loops, and a lot of the reasons why when you pull that button, when you push a button or pull a lever, you typically pull it in the wrong direction and make it worse. And that happens over and over again because people don't really understand how systems behave. Drift into Failure is a really bad book to be trying to read on an airplane, or if you're going to go into hospital soon. It's just, I was trying to read it on a plane, just have to put it down and read it sometime when you don't know anybody that's going on a plane, because it's got all kinds of plane crashes and why they happened and that kind of stuff. And then Everything is Obvious is a good book for understanding the sociology of how people interact with systems as well. So this is kind of sort of the interesting reading to go and figure out where this idea is coming from. If we put all this together, I really don't have time to go into this in detail, but we have a very sophisticated API architecture. There are presentations on this. If you look up RxJava or the functional reactive mode, this is straight out of Michael Nygaard's book. It's a very powerful way of building an API which is extremely resilient to failure and and it happens on the client side. So you build these circuit breakers that say, this thing doesn't appear to be working right. It automatically flips the circuit breaker, manages all that. So we've been building on that for a while. So in terms of our open source program, we have a few goals for it. We're trying to come up with the things we do. We think they're best practices. The only way you can find out is by putting them out there and discovering whether other people also think they're best practices. So kind of validating ourselves by putting our solutions out there. We're also using it to hire, retain, attract top engineering, and that has worked very well. So some of you may have heard of JClouds, the JClouds library. So Adrian Cockcroft, who built that over the last 3 years, joined us at the end of last year and is currently working on Denominator. So So we have 2 Adrian Cs now at Netflix, just to confuse people. It's also been building up the Netflix technology brand, which helps us attract interesting people. And then we're also getting the benefit of a shared ecosystem where more people are contributing to our code. They're finding out things we didn't know. They're adding things to it. We have, just to try and put it all together, we have lots and lots of individual projects. The little names, the odd names that are in red on here are all different pieces of the Netflix application. So we have client-side, server-side configuration things. And this is, think of this as the Google Reader replacement. It's not really got all the features for that. But if you wanted to build Google Reader out of the Netflix open source code base, we've already done most of the work for you as an example. So what's coming next? We're adding more features to this. We're filling in the gaps. But we're also starting to get more use cases. We're getting pull from people outside Netflix. And what that's giving us is a drive to more portability. So right now, this is a software base which we use on AWS. We don't try and run it anywhere else. It was optimized around high availability, high agility, and leveraging everything we could get out of AWS. But what we're trying to do here is build something more portable that's easier to deploy and take contributions from end users and also from vendors. And the vendors are taking this in some interesting places. There's interest in using this for enterprise private clouds and also from other public cloud vendors. But in particular, Eucalyptus, in the last build they did, said it's done when it runs Asgard. So they took our code and they added all the missing pieces and they tinkered with our code a little bit and they made something that actually works. They demonstrated this, and the next build will actually give you a place where you can run pretty much the core of our platform, but on an internally constructed system, cloud system. The Cloud Stack guys, they've got a few missing gaps, a few gaps as well. We typically build everything on top of autoscalers, as I mentioned. So that's the missing feature that most of the vendors have right now. And OpenStack as well. We've got interest from all of these different people. We're working with some of the vendors on each side. And we're trying to figure out, how do they extend their APIs to meet what we need, or how do we change our system to call into their APIs? So to boost this, we recently announced the Netflix Cloud Prize. These are some of the example things that we were trying to encourage. So we have 10 categories for contributions, and you basically, in about 6 months' time, will evaluate the best contributions on our GitHub pages where people have put all of the code that is the best monkey or the best portability enhancement or the best feature or whatever. And we're giving out prizes to those people and taking them to the conference, all expenses paid, all that kind of thing. So this is what it looks like. There's a 6-month process for getting it done. They get $10,000 each, and Amazon kicked in $5,000 of AWS credit, so you can go and build something and run it. And then we've got the entrants obviously have to conform to the rules. The rules are that everything here has to be Apache licensed and on GitHub. So there's no private code. It has to be open source code, and it has to be sitting on GitHub alongside all of the other code, and that's how we evaluate it. We'll be going through and figuring out what actually meets all these criteria. Then we have judges. There's 1 Netflix judge and 5 other judges from other companies to go and figure out which one's won. And then we'll take them to the AWS reInvent conference and put them on stage and give them some money, and they'll probably blow it all on the tables in Vegas. But that's their problem. At least we'll buy them dinner afterwards. So that's basically an idea for boosting open source adoption. We have 600-700 forks of the Cloud Prize. The first step in entering is to go to the Netflix Cloud Prize GitHub project and fork it. And once you hit that fork button, we can see who forked it. But you also have to register. There's a MailChimp form so that we know your email address, because there's no actual way to contact anybody on GitHub. So that's basically one of the ways we're trying to boost this whole thing. And just to summarize what's going on with Netflix OSS, we have functionality at scale now. What we're working on now is portability and trying to build an ecosystem around it. And this is a very rapidly evolving platform. Everything we do is in days or weeks. We don't really have much beyond it's like a 3-month window into the future of exactly what we're doing. And what I call this is a low mean time between an idea and making stuff happen. You know, the idea of denominator happened in January, the first code release was in February, and the first usable code at the beginning of March. And we've hit 1.0 now in April. So that's kind of a pretty rapid way of getting something done. So moving on briefly to some opportunities. This is sort of the section where I'm trying to think, what did I want to bring up that I thought the Linux Foundation, you know, what can you do for me maybe? And there's some things that I'm worried about in this architecture and in general. And one of them is monoculture, because what we do is we build this automation and we build the best thing we can build as a pattern, right? And so we have everyone running Linux, great. And everyone running Tomcat, that's all great. And that reduces the interaction complexity because now everything works with everything else because I've got fewer variants, right? But the problem with that is you get this, what I call an epidemic single point of failures. And this is like crop, not rotating, you know, everyone running the same genetically identical crop and then a disease gets in, wipes the whole thing out. And we've had a few examples of that in the last year or so. And what I call those is pattern failures. And the basic problems you get are infrastructure pattern failures, software stack, and application pattern failures. Infrastructure are the fairly obvious ones. You know, you get a bad batch of disks, bad batch of power supplies, a month in, everything in your data center starts dying at once, right? So typically there's enough mixture in the infrastructure that that kind of thing doesn't happen. We've seen sort of math errors in CPUs that after they've shipped, people find those kinds of issues from quite a while ago, but that kind of thing. So these are the sort of issues that I'm somewhat concerned about, but there's probably enough variation out there that I'm not too bothered. Software stack, there are time bombs. Like if you run something running for long enough, a counter wraps and it stops working, or you get a memory leak. There are date bombs like the leap year and the leap second, which was quite a worrying one. I'm sure you all are very aware of the leap second problem. And running out of an epoch timer, those kinds of things. We've seen issues where certs time out. We have one of our monkeys, a security monkey, or is it security? No, howler monkey. We have many monkeys. The howler monkey shouts a lot if the certs start timing out, and we've actually successfully managed to not run out, have that problem. Some other people have been fairly publicly having issues like that. We had a problem recently where one of the certificate authorities revoked something, and it broke a bunch of things for a while. And if you get a security exploit and you're running the same code everywhere, and that's the version that's got the exploit, all of a sudden you're exposed on a very wide front. And then language compiler, you know, if everything's written in the same language, obviously you're open to that too. On applications, what I call content bombs. So we once had a movie where the synopsis of the movie actually hung a thread in our code, and as that movie got displayed on more and more front ends, it just gradually took out our whole infrastructure. It's like infinite loop in some, you know, text handling code that had never seen that particular sort of thing go by before. So that's what I mean by a content bomb. The code is perfect until you put some different content through it, right? Configuration problems, versioning, and all these cascading failures. So what are we going to do about this? And one of the problems here is that because this is a monoculture and the patterns, the infrastructure and the automation is creating this monoculture. So what we can do is use the infrastructure to put diversity in there. So what I want to do is start automating the diversity management. Maybe I should be running 50% BSD and 50% Linux, or 50% CentOS and 50% Ubuntu on different versions of the kernel, and hope that whatever kernel bug turns up is only in one of those. You know, how much diversity do I actually need? But then my automation might break, so I kind of need diverse automation as well. I mean, we do that to some extent. We have two totally independent monitoring systems, so when one breaks, we can use the other one to see what's going on, for example. I mean, we only really need one monitoring system, but it's really good to have two when they break. And what you're really doing here is making a trade-off between efficiency and anti-fragility. And the more efficient you make something, you see this, it gets more and more efficient, and then suddenly it breaks horribly. Right? And it's the lowest cost way of doing something is the most fragile. And you have to figure out how much fat do you leave in the system so that you can skip a few meals and not keel over and die. Right? That's kind of one of the analogies here. The Anti-Fragile book by Taleb is a good summary of that. So let's just look at my sort of, from the outside, I'm not, a regular member of this group, so just trying to look at it from the outside, what do I think, some SWOT analysis for you guys. I mean, from Linux, from our point of view, it has ubiquitous support. Open source is the default. This is, everything we do is based currently, all of our infrastructure and all our code runs on Linux. And we're open sourcing everything. So that's a pretty good strength. I think there's a couple of things to pick at. Is maybe there's some gaps in networking versus BSD. Maybe it's just habit and people just think. Maybe it's perception, but there's probably something behind that perception. And I've stared at Wireshark traces and gone, this isn't really what the TCP spec says it's supposed to do here. Reading the code. This is what Linux is doing, and this is what the spec says it's doing. So there's a few places where it's not quite right. And I think observability, there's a few times where we're not quite sure what's going on, and if you're working in an environment where you expect everything to be broken, what's really important is to be able to tell that it's broken very quickly. So how fast can I find out that something isn't happy in this machine? And within the kernel, within all the layers of software around that, you want very good observability. You want to be exporting metrics that tell you the health of the thing and whether it's in a normal space or whether something strange is happening. I think there's opportunities here to optimize for these ephemeral dynamic use cases. I'm very interested in how fast I can boot up a machine because it's only going to run for an hour. So if it takes 10, 15 minutes to boot and start my app, then that's, I've wasted a long chunk of that time. And then threats, this is what I've been talking about here, epidemic failure modes. And the leap second nearly took us out. It took out several large sites on the internet. It took out some of our Hadoop clusters. We could have had a total outage on Netflix from that bug. And I noticed that some friends of mine that work at other places had a very bad day that day because their site wasn't even sending back anything. It just was like off the net, dead. So that's the kind of stuff that keeps me up at night anyway. So takeaway. What we're doing at Netflix is making it easy for everyone to adopt these cloud-native patterns by giving away the code that implements those patterns. And what I think you guys should be thinking about is how to optimize for this sort of dystopia and diversity of systems. So there's some links there. I'm happy to connect to anyone on LinkedIn and Twitter and whatever. So take some few questions now, maybe.
I think we have time for just 2 questions.
Yeah.
Adam, just shout it out.
Yeah.
This sounds like a great open source strategy. I'm just wondering, Java and Silverlight, does that play into that somehow? That's the client side, I guess, right?
The client side stuff, yeah, I mean, okay, so I'll take the standard question everyone always asks is, hey, why can't I play Netflix on my Linux box? And yeah, so that's the Silverlight. We're getting away from Silverlight. Right now, if you have a Chrome OS, we run on native HTML5 with the protected video tag that Google has implemented on Chrome OS. So you have to have one of those Chrome OS tablet thingies, whatever those are called, laptops. And who's got one? Hey, good. So that runs native Netflix with no plugin. And this is our path forward. We're trying to get to the point where we don't need a plugin and we're running that. But we have to have DRM, so you have to have the protected video tag. So if there's somebody from Google here from the Chrome team, okay, just put that in the browser and ship it to Linux, and then that's the solution we're working for. Okay, it should just be generic at that point that every browser that's running, that version of HTML5. So we're kind of on the edge of solving that particular problem. Finally, I know it's been a long, annoying thing for a long time. Anyone else?
As a follow-up question to that, even if it worked on Linux-based systems, you say, well, we have to have DRM. And I'd like to challenge that a little bit. I understand that that's an inevitability for you right now because you deal with the MPAA, but what is Netflix doing to help fight DRM entirely?
So right now, what we're basically doing is giving billions of dollars to Hollywood to buy the content so that they can afford to build more content. I mean, that's the business we're in. We're a major source of funds for Hollywood, and we're mostly concerned about getting content made and getting it out to our customers. We have to get our $8 a month for some reason, right? So if you can sign up for Netflix without paying us, then we don't have the money to pay to buy the content. So it's a commercial business, and that's the terms of the business that we're in. We don't have any way of working around that problem.
I don't think the problem is the $8 to get the $8. The problem is that if I'm going to copy the movie locally and store it.
Yeah, well, we just do streaming. We don't do...
My kid likes to watch the same movie over and over again. That's the DRM. The DRM is not the $8.
Sure. Well, we have, you can watch the movie as many times as you want, but we just do streaming for, there's a number of ways that Netflix's business model is very, very narrowly focused. And we don't do download, and we don't do all these other things. And by keeping the business and the functionality of what we build very, very narrow, it makes it easy for us to do the one thing that we are doing right now, which is to go global. So every time we go to a new country, every feature that we built would then have to be internationalized and localized and support and all that stuff. So right now, the Netflix product is being kept very narrow and simple because we haven't finished taking it completely global. And once we go global and we're in everywhere and we're licensing content for the whole world rather than just for one country at a time, and then we can look at adding features and doing more things. But this is a phase of our business where we're doing a global land grab. And every piece of tax we put on that slows us down. So that's kind of, from a business point of view, I think you could look at, if you could move 5 years into the future and look back, you'll see this is very much a development phase. And the end point we're shooting for is that we should have, everything for everybody in the world, and there'll be a lot more stuff there. But that we've got to get through this phase so that we can get to that.
All right. I'm going to have to end that. Thank you.